Imagine standing on your crush pad, looking at 1,000 pounds of Zinfandel that just arrived from the vineyard. Your pre-harvest field tests indicated you'd be processing 500 pounds at a manageable, optimal 24 degrees Brix.
Right.
Instead, the yield has doubled. And worse, as the grapes go through the crusher destemmer and the must begins to soak, you pull a sample and the chemistry is severely off. You are not looking at 24 Brix. You are looking at a massive 28 degrees Brix coupled with a highly unstable TH of 3.85.
Which is a critical situation for any practitioner.
Exactly. If you are managing this harvest, you know immediately that your yeast are about to face a toxic environment, and spoiled organisms are already finding an ideal vector. The question is, what is your precise protocol for triage?
Well, that specific scenario represents the dividing line between empirical, reactive winemaking and precision, data-driven enology. When you're faced with extreme field anomalies, sensory evaluation and guesswork are simply insufficient.
They fail entirely.
They do. You need a rigorous quantitative framework to correct the must chemistry, mitigate the biological risks, and ultimately secure your intended stylistic targets. Today, we are conducting a deep dive into the transition from craft to applied science, focusing on a specific suite of operational tools designed to completely remove estimation from the cellar.
We are basing our analysis today on two foundational pieces of documentation. The first is a comprehensive system titled Precision Winemaking at Your Fingertips, which details a series of web-based imological calculators developed by Michael and Sharon Orton.
It is worth noting that the Ortons operate a private laboratory and vineyard in Lincoln, California, bringing over 30 years of applied experience to this analytical framework.
Right. And the second source is the Winemaking 101 curriculum from Valley Vintner, which establishes the baseline chemical and volumetric parameters we need to reference. Our objective for you, the practitioner listening to this session, is to operationalize these quantitative tools.
Because theory must eventually meet operational reality.
Precisely. We are going to examine the exact mechanics of pH scaling, volumetric yield calculations, targeted nitrogen supplementation, and molecular sulfur dioxide stabilization. And we'll be using that 1,000-pound Zinfandel anomaly, which the Ortons documented as the Big Zin Challenge, as our practical case study.
To understand the severity of the deviation in that case study, we first need to establish the enological standards. The baseline parameters provided in our source material dictate specific chemical thresholds for optimal phenolic and physiological ripeness.
And these are inherently contingent upon the intended varietal style, correct?
Yes, strictly dependent on style. If you are producing red grape varietals, the standard target range for harvest is 23 to 26 degrees Brix. That specific concentration of soluble solids is required to yield a potential alcohol by volume, or ABV, of 13 to 15.5%.
Understood.
Concurrently, the target pH range is strictly situated between 3.4 and 3.7, with titratable acidity, or TA, measuring between 0.5 and 0.7 grams per liter.
Let's look at the reasoning behind those specific red wine parameters. We aren't just looking at sugar accumulation for the sake of alcohol production. We are looking for the intersection of sugar accumulation and phenolic ripeness.
The softening of the skin tannins.
Exactly. The tannins and the degradation of pyrrocines, which are those compounds responsible for harsh, green, vegetative characteristics. In red varietals, reaching that phenolic maturity often requires hanging the fruit longer, which naturally pushes the Brix up into that 23 to 26 range.
And naturally drives the pH higher as the malic acid respires in the berry during that extended hang time.
Right. Now, that is a critical distinction because the physiological targets for white grape varietals are fundamentally different.
They are, because the stylistic goals prioritize different chemical components entirely. For whites, the objective is to preserve the concentration of malic acid and protect the highly volatile aromatic precursors.
So you harvest earlier.
Precisely. Therefore, the targeted soluble solids are scaled down to 20 to 23 degrees Brix, which will result in a lower potential ABV of 11 to 13.75%. Because the fruit is harvested earlier, the pH targets are correspondingly more acidic, ranging from 3.2 to 3.4.
And the titratable acidity rests higher as well, between 0.6 and 0.8 grams per liter.
Correct.
Beyond establishing those chemical baselines, the documentation stresses the importance of standardizing your yield metrics for logistical planning. If you are calculating tank allocation, chemical inventory, and overall cellar logistics, you have to have a reliable baseline for volumetric conversion.
Because if your starting volume is an estimate, every subsequent chemical addition will be mathematically compromised.
Exactly. The Valley Vintner materials establish that 80 pounds of raw grapes will yield roughly 6 gallons of juice post-crush. After you account for the inevitable losses during primary fermentation, racking off the gross lees, and the aging process, that 6 gallons of juice nets out to 5 gallons of finished clarified wine.
And in standard packaging terms, that 5-gallon net yield equates to approximately 2 standard cases, or 24 bottles.
Right, and when we scale those metrics up to commercial operations, a full ton of grapes, 2,000 pounds, yields approximately 150 to 160 gallons of finished wine.
These conversion metrics are not merely administrative. They are the foundational data points required before you can even begin to apply the precision calculators. You cannot accurately calculate an acidulation dose or a nitrogen addition if your initial volume estimates are fundamentally flawed.
Which brings us back to the crush pad and the big Zin deviation. Let's dissect the anatomy of this anomaly. The logistics plan was built around an anticipated harvest of 500 pounds of Zinfandel. Pre-harvest field tests indicated the soluble solids were sitting just below 24 degrees Brix, which, as we established, is perfectly aligned with the optimal red varietal parameters.
That was a very standard, manageable target.
But the physical yield upon arrival was over 1,000 pounds. And crucially, post-crush analysis revealed that the must soaked out to a reading of 28 degrees Brix alongside an unstable pH of 3.85. What causes that kind of massive discrepancy between a field sample taken just days prior and the actual must chemistry in the bin?
Well, the phenomenon of the soak-out is a well-documented challenge, particularly with varietals prone to uneven ripening, such as Zinfandel. The discrepancy arises from dehydration and raisoning on the vine.
So the field test is essentially missing data.
Exactly. When you conduct a field test, you are typically sampling intact, turgid berries. The refractometer reads the sugar concentration of the free-flowing juice. However, hidden within those clusters are desiccated berries and raisins that contain highly concentrated crystallized sugars.
Which don't release their sugar during a gentle field pressing.
Right. But during the physical crush and the subsequent 24 to 48 hours of maceration, these raisins rehydrate. As they absorb moisture from the surrounding juice, they release those bound sugars into the must matrix, causing a rapid artificial spike in the overall Brix reading.
And the pH?
Simultaneously, the inclusion of those overripe dehydrated berries contributes to a significant upward shift in the pH.
That leaves the practitioner with a must that is severely out of physiological balance. Let's examine the biological implications if we were to proceed with this must as is. If I attempt to pitch yeast into a 28 Brix environment, what is actually happening at the cellular level to the Saccharomyces cerevisiae? I know we are talking about osmotic stress, but how does that physically manifest and disrupt the fermentation kinetics?
The disruption occurs through a process called plasmolysis. A must at 28 degrees Brix is a severely hypertonic environment. The concentration of solutes, the sugars outside the yeast cell, is significantly higher than the concentration inside the cell.
Right, so osmotic pressure takes over.
According to the principles of osmosis, water will rapidly move across the semi-permeable lipid bilayer of the yeast cell membrane from an area of low solute concentration to an area of high solute concentration. The hypertonic must literally draws the intracellular water out of the yeast.
So the yeast cells are essentially dehydrating in the liquid.
Precisely. As the intracellular water exits, the yeast vacuole shrinks and the plasma membrane pulls away from the cell wall. This halts their enzymatic pathways and prevents cell division.
Resulting in sluggish kinetics.
Very sluggish. You will observe an incredibly sluggish onset of fermentation, a failure to build adequate biomass, and ultimately a very high probability of a stuck fermentation before dryness is achieved, leaving you with residual sugar and a microbiologically unstable wine.
And compounding that osmotic stress is the pH factor. We are sitting at a pH of 3.85. We know that higher pH environments drastically reduce the efficacy of sulfur dioxide, which we will detail later when we discuss molecular SO2. But practically, in the immediate pre-fermentation phase, a 3.85 pH minimizes the antimicrobial protection in the must.
It maximizes the vector for spoilage organisms like Acetobacter or wild yeasts.
Right, and it accelerates the rate of enzymatic oxidation, threatening the color and aromatic stability before fermentation even begins.
Fermenting under those parameters without intervention guarantees structural and microbiological flaws in the finished wine.
So triage is required.
Triage is absolutely required. The strategy designed by the Ortons involved a complete divergence from standard operational procedure. They split the 1,000-pound aggregate into two distinct 500-pound batches, each estimated to yield roughly 35 gallons of must, based on our standard conversion metrics.
And batch 1 was designated for correction.
Correct. The goal was to manipulate the chemistry back into the baseline parameters to produce a full-bodied dry red Zinfandel while incorporating a Say-Nay protocol to yield a rosé fraction.
And batch 2 took a completely different path. Instead of fighting the extreme chemistry, they utilized it.
Yes. Batch 2 was redirected from a standard dry fermentation toward a fortified high residual sugar application, a dessert wine. We will analyze the specific mechanics of that fortification later in the session, but first, we need to detail the precise mathematical interventions required for batch 1.
Let's focus on the correction protocols for batch 1. We have 35 gallons of must. The immediate analogical requirement is twofold. We must reduce the soluble solids from 28 degrees Brix to a viable, fermentable 24 degrees Brix.
And we must concurrently acidulate the must to drop the pH from the unstable 3.85 down to a protective target of 3.55.
Which requires precise calculation regarding dilution and acidulation. According to the documentation, utilizing the water addition calculator to determine the required dilution for a 35-gallon batch to shift from 28 to 24 Brix generated an exact output, 5.8 gallons of water.
The mathematics of dilution are straightforward, yes, but the subsequent acidulation protocol introduces significant chemical complexity. Using the tartaric acid addition tool, achieving a drop of 0.30 pH units moving from 3.85 down to 3.55 required an addition of exactly 394.4 grams of tartaric acid.
To understand this specific calculation, we need to analyze the industry standard metric known as the rule of 1.0. This baseline rule dictates that adding 1.0 gram of tartaric acid per liter of must will lower the pH by approximately 0.1 units.
However, the documentation is very clear that the rule of 1.0 is merely a guideline, not an absolute constant. The actual pH shift is highly dependent on the must's innate buffering capacity.
Right. How should we visualize this buffering capacity? If I add tartaric acid, why doesn't the pH drop immediately in a linear fashion? What is pushing back against the acidulation?
The most accurate way to conceptualize buffering capacity is to think of it as a chemical sponge within the must. Grape juice contains natural minerals, primarily potassium ions, which have been drawn up from the soil through the vine.
Understood.
When you add tartaric acid to the must, you are introducing hydrogen ions, which should lower the pH, and tartrate ions. However, instead of remaining free in solution to lower the pH, those tartrate ions immediately bind with the available potassium to form potassium bitartrate.
Which is the compound that eventually precipitates out as tartrate crystals or line diamonds, correct?
Exactly. This precipitation reaction neutralizes a significant portion of your acid addition. The chemical sponge is soaking up the tartaric acid before it can effectively lower the pH. The precision calculators are designed to account for this buffering resistance.
And they differentiate between pre-fermentation must and post-fermentation wine, correct?
They do, mathematically. Pre-fermentation must has a very high buffering capacity because the concentration of potassium is at its peak. You require a much larger dose of tartaric acid to break the buffer, saturate the sponge, and finally achieve the downward shift in pH.
And post-fermentation, that buffering capacity is reduced.
Significantly reduced. During fermentation, the rising concentration of ethanol decreases the solubility of potassium bitartrate. A large percentage of those buffering minerals naturally precipitate out of solution during primary fermentation.
I see.
Therefore, if you are attempting to acidulate a finished wine, the chemical sponge is much smaller, and you require a significantly lower dosage of tartaric acid to achieve the same 0.1 unit drop in pH. The distinction is vital for preventing overcorrection.
So in our case study, acting on the pre-fermentation must, the 394.4 gram addition was precisely calibrated to overcome the heavy potassium buffering of the Zinfandel and secure the 3.55 target.
Precisely.
This brings us to a major technical trade-off, and one that any experienced practitioner would immediately flag. We are talking about adding nearly 6 gallons of water to a 35-gallon batch of must.
It's a massive volumetric shift.
It is. While that 5.8-gallon water addition successfully corrects the osmotic pressure and aligns the potential alcohol, it severely dilutes the overall matrix. Specifically, it dilutes the skin-to-juice ratio. By increasing the liquid volume without increasing the mass of the grape skins, you are directly compromising the density of anthocyanins, which govern your color stability.
And you are diluting the concentration of tannins.
Right, which form the foundational structural matrix and dictate the wine's aging potential. You've fixed the chemistry, but you've potentially hollowed out the wine.
That is the inherent risk of large-scale water additions. To mitigate this volumetric dilution, the operational protocol required an immediate countermeasure, a precision saignée or juice bleed.
A bleed to restore the balance.
Correct. By balancing the required water addition with an equivalent volumetric extraction of juice prior to fermentation, you effectively restore the optimal skin-to-juice ratio. The math dictates that to offset the 5.8-gallon water addition, you must remove exactly 5.8 gallons of free-run juice from the must before the water is integrated.
Executing a precise 5.8-gallon bleed requires meticulous fractional volume management. In a large-scale industrial facility, you would simply rely on integrated inline flow meters.
But for the practitioner utilizing standard chiller equipment, pulling an exact volume requires calculating the internal geometry of the receiving vessel.
Which brings us to the tank fill calculator. The Orton documentation outlines the application of this specific tool. The data inputs were derived from the physical dimensions of the receiving vessel being used for the saignée. In this case, a 100-liter cylindrical tank measuring 16.25 inches in diameter and 29.5 inches in height.
The operational geometry here relies on calculating the total volume of the cylinder and converting those cubic inches into standard liquid gallons. A standard U.S. gallon is defined as 231 cubic inches.
Right.
By inputting the tank's radius and total height, the calculator determines the specific liquid depth required to achieve the target volume. To extract precisely 5.8 gallons into that specific 100-liter tank, the liquid height from the bottom of the tank needed to reach exactly 6.4 inches.
The calculator also provides an alternative measurement, which is often more practical: ullage.
Yes, measuring from the bottom up can be difficult depending on the opacity of the tank material. The calculator also provides the ullage, which is the measurement of the empty headspace from the rim of the tank down to the surface of the liquid.
And for this extract,
a 6.4-inch liquid height correlates to an ullage of 23 inches. This allows the operator to insert a sanitized measuring rod from the top and execute a perfectly precise transfer simply by monitoring the headspace.
Now we have 5.8 gallons of free-run juice separated from the primary batch. This extracted juice possesses the original anomalous field parameters: 28 degrees Brix and a 3.85 pH. Rather than discarding it, this volume was repurposed into a rosé fraction.
However, this secondary volume now requires its own distinct chemical correction protocol.
Because the stylistic parameters for a rosé are quite strict. The style demands a lower final alcohol concentration and a higher, crisper acidity profile to ensure freshness. The specific stylistic target established for this rosé fraction was 24 degrees Brix and a much crisper pH of 3.45.
Operating on this isolated 5.8-gallon volume, the precision calculators were deployed a second time. To correct the saignée to those specific rosé targets, the protocol dictated an addition of 0.97 gallons of water to adjust the Brix and a subsequent addition of 102.5 grams of tartaric acid to overcome the buffering capacity and reach the 3.45 pH target.
So the addition of that 0.97 gallons of water brings the final corrected volume of the rosé fermentation batch up to 6.77 gallons.
Correct.
The compounding complexity here is fascinating. By applying these specific volumetric and chemical calculations, the practitioner ensures that both the 35-gallon primary red fermentation and the 6.77-gallon secondary rosé fermentation begin with completely optimized, stable chemistry.
And that is the core objective of the methodology. It completely removes estimation from the process, establishing a secure chemical foundation before you even introduce the biological variables.
With the chemical and volumetric parameters now stabilized across both fractions, the operational focus shifts to managing the biology. Specifically, we need to analyze yeast assimilable nitrogen, or YAN, and how it dictates fermentation kinetics. Managing your YAN is critical under any circumstances.
But it becomes exponentially more important in high-Brix environments.
Exactly. Even though we've diluted the must down to 24 Brix, the metabolic demands placed on the yeast population are significant given the total volume of sucrose that must be converted and the eventual onset of ethanol toxicity.
Right.
According to the case study, the vineyard source for the Zinfandel could not supply historical YAN data. If you are sourcing external fruit and lack access to immediate laboratory analysis, how do you establish a baseline for your nitrogen protocol?
Well, in the absence of specific chemical analysis, the protocol dictates adopting a worst-case scenario posture. The documentation necessitated a conservative baseline estimate of 80 parts per million of yan.
And from an enological perspective, an initial yan of 80 ppm is considered highly deficient.
Highly deficient. Without intervention, a must at 80 ppm will inevitably lead to yeast starvation, the production of hydrogen sulfide, which manifests as that distinct rotten egg odor, and eventually a stuck fermentation. A structured, precise nutrient regimen is mandatory.
The YN and nutrient calculator determines the total nitrogen addition required based on 3 integrated variables: the specific strain of yeast selected, the starting Brix concentration, and the total volume of the must.
Let's analyze the yeast strain selection, as it's a primary variable in the calculation. For the rosé fraction, the protocol selected the QA23 strain, which is noted for its low nitrogen requirement and ability to enhance aromatic expression. For the full-bodied primary Zinfandel, the 1118 strain was chosen, which also operates efficiently on lower nitrogen levels and is highly tolerant of ethanol.
And for batch 2.
Conversely, the fortified Zinfandel batch 2, utilized the D254 strain, a yeast that demands a medium level of nutrient supplementation.
The strain selection directly dictates the output of the YN calculator. Once a specific nitrogen target is generated, the protocol establishes a highly structured feeding schedule. It differentiates explicitly between the initial stages of yeast development and the specific types of nitrogen being applied. The first phase is rehydration.
During the rehydration of the desiccated yeast, a specific nutrient complex, such as GoFerm, is utilized in the warm water suspension.
It is essential to highlight a specific point from the documentation regarding rehydration nutrients. The nitrogen provided during this phase does not count toward the overall calculated yan target for the primary fermentation. Why is that distinction made?
Because the physiological objective during rehydration is entirely different. The nutrients in GoFerm are primarily designed to build the structural integrity of the yeast cell before it is subjected to the osmotic stress of the must.
So it's about fortification, not feeding.
Exactly. The focus is on synthesizing vital cell membrane sterols and unsaturated fatty acids during the initial blooming phase. While there is some trace nitrogen present, it is utilized internally for this structural development, not for the expansive biomass production required once the yeast is pitched into the must.
Therefore, you must exclude it from your total yan calculation to avoid underfeeding during the active fermentation. Once the yeast is pitched, the actual YN additions are split, utilizing both organic and inorganic nitrogen sources. The protocol is incredibly strict regarding the sequence and timing of these additions. Organic nitrogen, which typically takes the form of deactivated yeasts like fermate-O, is administered early in the fermentation process.
Its primary function is to build the initial yeast biomass slowly and steadily.
While inorganic nitrogen, specifically diammonium phosphate, or DAP, is reserved strictly for the active growth phase when the yeast are rapidly multiplying and require highly accessible, fast-acting nitrogen.
The yan calculator specifies a split feeding schedule. The first organic addition occurs 24 hours after pitching the yeast, and the second addition, the inorganic DAP, occurs precisely at the 1/3 sugar depletion mark.
The timing of that second addition is an area that requires intense technical scrutiny, particularly for practitioners transitioning to a data-driven approach.
It is often misunderstood, yes.
Let's explore that. The documentation establishes an absolute rule. DAP must never be added after the must has crossed the threshold of 1/3 sugar depletion. Now, if I am observing a fermentation and I notice the kinetics slowing down significantly at the halfway point, the cap isn't pushing as hard, the temperature is dropping, the empirical inclination of many winemakers might be to add more nitrogen.
The logic seems sound, empirically.
The yeast look like they are struggling, so I should feed them more DAP to reinvigorate the biomass and push them to dryness. Why is that inclination biologically flawed?
It is biologically flawed and operationally dangerous due to the physiological shifts occurring within the Saccharomyces cerevisiae as the environment changes. Inorganic nitrogen, like DAP, cannot simply diffuse into the yeast cell.
It needs a mechanism.
It requires active transport proteins embedded in the cell membrane to shuttle the ammonium ions inside. As the fermentation progresses past the 1/3 depletion mark, the concentration of ethanol in the must begins to rise significantly, and ethanol is fundamentally toxic to yeast.
And that toxicity specifically targets those transport proteins.
Precisely. The accumulating ethanol physically alters the lipid bilayer of the yeast cell membrane and specifically inhibits the function of those active transport proteins. The yeast lose the physiological capacity to assimilate the inorganic nitrogen.
I see.
You can pour as much DAP into the tank as you want, but the yeast are physically locked out from consuming it.
So adding inorganic nitrogen late in the fermentation process provides zero benefit to the
It provides absolutely zero benefit, yes,
Right.
and it actually creates a significant hazard.
Right, because the yeast cannot assimilate that excess DAP. It remains suspended in the wine matrix. You have essentially created a nutrient vector for spoilage organisms. Specifically, you are providing an optimal, highly available food source for Brettanomyces or lactic acid bacteria during the elevage phase.
You are setting a biological time bomb that will drastically increase the risk of microbial taint in the cellar.
That is the exact mechanism of failure. The precision of the YN calculator ensures that the biomass receives exactly the parts per million of nitrogen it can assimilate during its active growth phase, and not a gram more.
This discipline prevents the creation of a nutrient-rich environment post-fermentation. Managing your nitrogen with mathematical precision is not just about ensuring a clean primary fermentation. It is an essential protocol for long-term stability in the barrel.
That concludes the correction and biological management of batch 1. We will now pivot our analysis to the management of batch 2, the second 500-pound lot from the Big Zin harvest.
As we established earlier, the enological objective for this batch was entirely different.
The Ortons decided to produce a dessert-style Zinfandel. To achieve this, the practitioner must artificially arrest the fermentation process prior to dryness, aiming to yield a finished wine with a target of 18% ABV and approximately 10% residual sugar, or RS.
Executing this requires highly accurate, real-time monitoring of the active fermentation to determine the exact moment to halt microbial activity.
Monitoring a rapidly fermenting high brix must present significant mechanical challenges on the crush pad. The traditional approach utilizes a hydrometer.
However, hydrometers require large sample volumes to float the instrument. They generate excessive waste if you are testing multiple times a day, and they are cumbersome to utilize frequently during an active cap management cycle, especially when the must is thick with skins and seeds.
Right. So the operational protocol detailed in the documentation dictates the use of an autothermal compensation, or ATC, refractometer.
The refractometer offers a massive mechanical advantage in terms of efficiency. You only require a few drops of must for an instant reading, which you can easily pull during a punchdown.
And the ATC functionality eliminates the need for manual temperature corrections, which is critical because an active fermentation generates significant exothermic heat, and temperature fluctuations will wildly skew a standard specific gravity reading.
However, while the mechanical application is simpler, utilizing optical refractometry during an active fermentation introduces a complex problem rooted in chemical physics. We must understand exactly what the instrument is measuring.
It measures the refractive index?
Yes, a refractometer measures the refractive index of a liquid, essentially the specific degree to which light bends or refracts as it passes through the sample. In unfermented pristine must, this bend is caused entirely by the density of the soluble solids, the sucrose.
But once you pitch the yeast and fermentation initiates, the chemical composition of the liquid begins to change rapidly. The yeast are converting that sucrose into ethanol. And ethanol has a fundamentally different refractive index than sugar water.
Exactly. To conceptualize this, think of the optical interference like looking through a distorted lens or a mirage on a hot road. The light is being bent by two different substances simultaneously.
The sugar and the alcohol.
Right. As the alcohol concentration rises in the fermenting must, it bends the light in a way that artificially inflates the brix reading. It tricks the lens of the refractometer. A direct refractometer reading of an actively fermenting must will never accurately reach zero, even if the wine is bone dry. The optical interference of the accumulated alcohol continually skews the data upward.
To extract accurate, actionable data from that skewed reading, algorithmic compensation is required. The practitioner cannot simply read the lens. They must run the data through the brix and specific gravity calculator.
This calculator utilizes a standardized enological algorithm to mathematically strip out the optical effect of the ethanol, revealing the true density of the remaining sugar in the liquid.
To run the calculation, the protocol requires two data inputs. The starting brix of the unfermented must, which in the case of batch 2 was the anomalous 28 degrees, and the observed refractometer reading taken during the active fermentation, which the documentation refers to as the AB value.
Reviewing the operational data from the case study, let us trace the mathematics. During the active fermentation of batch 2, a sample was pulled, and the observed reading on the refractometer, the AB value, was 17.4 degrees Brix.
If a novice practitioner were to accept that reading at face value, they would assume the fermentation still had a massive amount of sugar left to convert.
However, by inputting the starting Brix of 28 and the observed Brix of 17.4 into the calculator, the algorithm applied the correction factor. The true adjusted Brix was calculated at exactly 10.1 degrees.
And in terms of practical application, an adjusted reading of 10.1 degrees Brix correlates directly to approximately 10.1% residual sugar in the must.
This calculation signaled to the operators that the stylistic target of 10% RS had been achieved, and immediate intervention was required.
Before we discuss the fortification, we can further apply conversion mathematics to this adjusted reading to determine the exact alcoholic status of the base wine at that specific moment.
Let's run those numbers.
Starting at an initial 28 degrees Brix and dropping to an adjusted true Brix of 10.1 degrees indicates that exactly 17.9 degrees of Brix were consumed and converted by the yeast.
To determine the alcohol generated by that conversion, we utilize a standard enneological conversion factor of 0.6. This metric states that the conversion of 1 degree of Brix yields approximately 0.6% alcohol by volume.
By multiplying the 17.9 consumed Brix by the 0.6 conversion factor, we calculate that the base wine had achieved approximately 10.74% ABV at the exact moment the 10% residual sugar target was hit.
And at this stage, the base wine is immediately pressed to separate the liquid from the gross solids.
With the base wine pressed, sitting at 10.74% ABV and roughly 10% residual sugar, the fermentation is still technically active, albeit separated from the skins. The next operational step is fortification.
The enological objective here is to instantly and violently shift the alcohol concentration of the matrix from the current 10.74% up to the stylistic target of 18% ABV.
This massive spike in alcohol is required to permanently halt all microbial activity and chemically secure the residual sugar, preventing any further fermentation in the barrel or the bottle.
Executing this fortification with exact precision relies on an application known as Pearson's square. Pearson's square is an algebraic calculation utilized across the beverage and dairy industries to determine the exact volumetric requirements for blending two solutions of differing concentrations to achieve a specific intermediate target concentration.
In this application, the calculation requires inputting the base ABV of the pressed wine, which we establish at 10.74%, and the ABV of the fortifying spirit. The protocol identifies the fortifying agent as a 95% neutral great spirit.
The application of the Pearson square algorithm cross-references those variables against the target volume and the target 18% concentration. It calculates the required addition with absolute, infallible precision.
The output from the calculator dictated an exact volumetric addition of 3.3 gallons of the 95% spirit to the active base wine.
The physical integration of that 3.3 gallons of high-proof spirit instantly elevates the overall concentration of the entire batch to the 18% threshold. You must consider the biological impact of this addition.
The osmotic shock.
Yes, at 18% ABV, the osmotic and toxic stress placed on the lipid bilayer of the Saccharomyces cerevisiae is absolute. Cellular function ceases immediately. The transport proteins denature, and the yeast are rendered completely inert.
This precise application guarantees the microbiological stability of that 10% residual sugar throughout the entirety of the aging process.
It is a definitive microbiological halt.
Following the conclusion of primary fermentation for both the corrected dry fractions and the fortified dessert fraction, the operational focus transitions to the elevage phase. The post-fermentation protocol details a rigorous sequence of physical and chemical parameters required for long-term aging.
The physical management begins with a settling period of up to 2 weeks, allowing the gross lees, the dead yeast cells, heavy pulp and tartrate precipitates, to fall to the bottom of the vessel.
This is followed by carefully racking the clarified wine off those gross lees and transferring it into appropriate aging vessels, which may be traditional oak barrels or inert glass carboys.
A critical physical parameter of this cellaring phase is the meticulous maintenance of topped-up vessels. The practitioner must mathematically account for evaporation.
The angel's share.
Exactly. In a standard cellar environment, the annual evaporation rate from a traditional oak barrel is approximately 10% of the total volume. As the water and ethanol evaporate through the staves, ullage, or empty headspace is created inside the barrel.
This headspace is immediately filled with ambient oxygen. Diligent, scheduled topping of the barrels is mandatory to displace that oxygen, minimize the headspace, and prevent excessive oxidative exposure.
because that exposure would prematurely age the wine and facilitate the growth of aerobic spoilage organisms like Acetobacter.
Parallel to this strict volume management is the chemical management of the wine's structural matrix, specifically the integration of tannins. The protocol outlines several operational options depending on the stage of production. It differentiates between sacrificial tannins and aging tannins.
Sacrificial tannins, which typically take the form of highly pulverized oak dust or small chips, are frequently deployed directly into the must during primary fermentation.
Their function is entirely structural, not stylistic.
Correct. They are not intended to impart complex flavor profiles. Rather, they act as immediate binding agents, assisting in the early extraction and chemical stabilization of the anthocyan color compounds before they can precipitate out of the must.
Moving into the aging phase, the protocol shifts to alternatives designed for structural integration and flavor development. These include oak cubes, spirals, staves, or the utilization of traditional barrel aging incorporating specific grain structures from French, American, or Hungarian oak.
The selection among these alternatives is heavily governed by their specific surface area to volume ratios.
Which dictates the extraction kinetics.
Precisely. The speed and intensity at which specific oak esters, lactones, and complex tannins integrate into the wine matrix. A spiral, for example, offers a massive surface area relative to its volume, resulting in a rapid, aggressive extraction over a matter of weeks, whereas a traditional barrel provides a slow, micro-oxygenated extraction over a period of years.
However, while tannin integration dictates the structural quality of the wine, the absolute most critical aspect of the elevage phase is the maintenance of long-term microbiological stability. This is achieved through precise molecular SO2 targeting.
The source documentation is explicit on this front. Relying on static, generalized sulfur dioxide dosing charts is chemically inadequate and operationally dangerous.
The protocol demands the strict use of the SO2 calculator to determine the specific additions of potassium metabisulfite, or KMS. The documentation establishes rigorous targets based on the varietal style. The target is 0.5 milligrams per liter of active molecular SO2 for red wines, and a mathematically higher target of 0.8 milligrams per liter for white and rosé wines. Why do whites and rosés require a higher threshold of protection?
The discrepancy in the targets relates back to the innate structural matrix of the wine. Red wines possess a high concentration of polyphenols, tannins, and anthocyanins extracted during the extended maceration on the skins.
Right.
These polyphenolic compounds naturally possess antioxidant properties. They provide the red wine with an innate chemical defense against oxidation. White wines and rosés, having minimal skin contact, completely lack that dense polyphenolic protection.
They are structurally naked.
They are. Therefore, they require a higher concentration of active molecular SO2 to achieve the same level of oxidative and antimicrobial stability.
The necessity of utilizing the calculator rather than a static chart lies in the complex variables that actually dictate the efficacy of the sulfur dioxide once it is introduced into the wine. Let's dive into the chemistry of those variables. The first and most impactful variable is the pH of the wine. We need to explore the exact relationship between pH and SO2. Why does a shift in pH fundamentally alter the protective power of your sulfite addition?
The relationship is governed by a chemical equilibrium. When you add KMS to a wine, it dissolves and yields free sulfur dioxide. However, that free SO2 exists in three different forms depending on the pH.
Which are?
It exists as bisulfite, sulfite, and molecular SO2. Molecular SO2 is the only form that is volatile and possesses actual antimicrobial and antioxidant properties. It is the only form that protects the wine.
Understood.
The equilibrium between these forms operates on a strict logarithmic curve relative to the pH. As the pH of the wine rises, the percentage of the free SO2 that exists in the active molecular state drops exponentially.
So as the wine becomes less acidic, the protective power of the SO2 vanishes into inactive forms.
Yes, exactly. To illustrate the severity of this logarithmic curve, a wine resting at a pH of 3.8 requires a mathematically massive dose of total free SO2 to yield just 0.5 milligrams per liter of the active molecular form compared to a wine resting at a pH of 3.4.
If you use a static chart and apply a standard 30 ppm dose across all your barrels, the barrel at 3.4 pH will be perfectly protected, while the barrel at 3.8 pH will be completely exposed to spoilage.
Which is why the calculator is indispensable.
The second critical variable that the calculator must account for is the alcohol by volume, the ABV. We must analyze why the alcohol percentage necessitates a sliding scale for KMS dosing. What is the synergistic relationship between ethanol and molecular SO2 regarding microbial stability?
The relationship revolves around cellular stress. Alcohol functions as a potent co-preservative within the wine matrix. High concentrations of ethanol physically stress and degrade the lipid bilayer of the cell membranes in potential spoilage organisms, such as Brettanomyces or Pediococcus. Because the organisms are already structurally compromised and struggling to survive the alcohol toxicity, they require far less molecular SO2 to definitively halt their metabolism. Therefore, a Zinfandel resting at 15% ABV requires mathematically less molecular SO2 to achieve complete microbiological stability than a Pinot Noir resting at 11% ABV, even if their pH values are completely identical.
The precision calculator automatically integrates the inverse factor of the alcohol concentration against the logarithmic curve of the pH. It processes these competing variables to determine the exact targeted parts per million of free SO2 required for that specific vessel.
And finally, it calculates the physical dose of KMS powder required to hit that exact target.
And there is one final crucial variable built into that calculation regarding the chemical itself. It is essential for the practitioner to remember that your standard commercial KMS powder is not 100% pure sulfur dioxide.
That is a very common point of operational failure. Potassium metabisulfite powder is a chemical compound. It is only roughly 57.6% available sulfur dioxide by weight.
If a practitioner calculates that they need 10 grams of SO2 and simply weighs out 10 grams of KMS powder on the scale, they are vastly underdosing the wine.
The calculator automatically factors this 57.6% purity constant into its final output, providing the exact gram weight of the physical KMS powder required for the specific volume of the vessel.
The integration of all these variables, the logarithmic pH curve, the co-preservative effect of the ABV, the total liquid volume, and the chemical purity constant of the KMS ensures that the wine is absolutely protected without the risk of oversulfating.
And avoiding oversulfating is critical. Excessive molecular SO2 will aggressively bleach the anthocyanin color compounds, stripping the visual density of the wine, and it will introduce harsh, metallic, struck-match sensory characteristics to the palate.
It is the synthesis of this rigorous methodology that ultimately defines precision enology. By utilizing this suite of interconnected calculators, the practitioner successfully removes estimation from the cellar environment.
Whether you are actively triaging extreme field anomalies like the Big Zen challenge on the crush pad, or you are managing the routine, granular chemistry of the multi-year elevage phase, winemaking shifts from a posture of reactive mitigation to one of proactive, authoritative command over the variables.
The operational tools detailed in this protocol, from correcting massive osmotic pressure through precise dilution and Sainet balancing, to strictly managing organic and inorganic nitrogen assimilation pathways, to achieving absolute microbiological stabilization targets through molecular chemistry, provide the specific framework necessary to ensure that the final product consistently reflects the intended stylistic parameters of the winemaker,
irrespective of the chaotic initial harvest conditions presented by the vineyard. By applying these principles, you insulate your production from the vagaries of the vintage, ensuring consistency, structural integrity, and long-term stability across your entire portfolio.
As we conclude this deep dive into precision enology, we must step back and consider an advanced theoretical implication of this methodology for you, the practitioner. If you now possess the absolute tools to perfectly manipulate must chemistry diluting runaway sugars, strictly correcting pH buffers, supplementing exact nitrogen deficiencies, and extracting specific volumetric fractions to hit exact mathematically perfect quantitative targets, at what point does this level of supreme overcorrection begin to homogenize the terroir?
It's a valid philosophical question.
You must evaluate the precise threshold in your own production facility where vital chemical intervention ceases to be a necessary stabilization measure and instead begins to overshadow the varietal typicity and the unique, unrepeatable physiological signature of the vineyard itself. Where does the science end and the fingerprint of the vintage begin? That is the balance you must strike.